Right. Our next speaker is Eyal Markman from UMass Amherst. We'll talk about semi-regular, secant, sheaves, and vague classes on abelian varieties.
Thank you very much for the invitation. So I apologize for those that may have heard this talk several times. I'll explain all the terms. Secant sheaves is I coined this term. It's sheaves whose germ character belongs to some secant to a trilorial variety. To the right, it show up soon. Okay, what are abelian varieties of Weil-type? So, definition. I only have a lot of time, so I'll skip it. But it's an invariant of the triple, and it belongs to the multiplicative group of rationals modulo. So the determinant will be rational, but then it will depend on a choice of the k basis of H1 of A with k coefficients because it's k vector space like this. And so to eliminate the dependence on the basis, you mod out by the norms of the multiplicative group of K. And now this is an invariant, and these three discrete invariants completely determine the component upwards logic. So, all right, so the main theorem 2025 is that the Weil classes are algebraic for all polarized abelian varieties of Weil-type, where the dimension of A is 6, and this discriminant invariant is -1. These are called of split type, and the exact value doesn't matter. It matters that there is one component for which all are algebraic. And I'll explain the ingredients that goes into the proof of this theorem, which is the main theorem. But it has important corollaries. So it follows. Oh, maybe before. I wish I had blue. Let's see if this works. This was proven by Chad, by Shen, for Q square root of -3, and by Koike for Q of square root of -1. And a corollary of this theorem is that so this Weil class that does not depend on the polarization, just the discriminant depends. So the Weil classes are algebraic for all abelian fourfolds of Weil-type. And this is all imaginary quadratic number field and all discriminant. Why is that? Because you specialize in the moduli space to an abelian sixfold, which is a product of a fourfold and a surface. And then it turns out that all discriminant fourfolds with all possible and the same K acts on both factors. And then all discriminant appear, fourfolds with all possible discriminant appears because the discriminant invariant is multiplicative under a Cartesian product. And so you can adjust the discriminant of the surface. And then if you pull back a divisor class from the surface, cap it with a V class and push forward to the fourfold, you'll get the V class. And so if they are algebraic on the sixfold, there will be algebraic on the fourfold factor. And so you get this. And so, then a corollary, so this is corollary 1. Corollary 2 of corollary 1 is that the Hodge conjecture holds for abelian varieties of dimension less than or equal to 5. So for up to 3, the Hodge conjecture is true for all projective smooth projective varieties. For fourfolds, Moonen and Zachin proved that the Hodge ring of abelian fourfolds are generated by divisor classes and V classes for possibly more than one complex multiplication, for more than one embedding of different fields. And so it follows, since the V classes are algebraic, the Hodge conjecture follows. For fivefolds, if they are simple, they are not isogenously to a product, then Telkev proved that the Hodge ring of every simple abelian variety of prime dimension is generated by divisor classes. And if they are not simple, Moonen and Zachin again proved that then the Hodge ring is generated by divisor classes and pullback of V classes from quotient abelian fourfold. And so again, everything boils down in this dimension to V classes. That's why they're so important. So that's, are there any questions? In the rest of the talk, I would like to describe the ingredients that go into the proof of this. This theorem. And so the strategy is to exhibit the algebraicity of the V classes on some special abelian sixfold, and this strategy is in all dimension. Just that I can implement it only for fourfolds and sixfolds. I would love to do it for eightfolds, and I'm working on it, but not yet successful. So, so prove the algebraicity for one special abelian sixfold, and then use the semi-regularity theorem to deform the algebraic cycles to all abelian sixfold in modular theta. And so I shall describe next the semi-regularity theorem. And this is a deformation theory conference, and this is the deformation theoretic ingredient, which is the main tool of the proof. And so this is due to originally a Bloch, and then it was generalized by Buchweitz-Flenner. So let Y be an n-dimensional smooth projective variety, and let E be a coherent sheaf on Y. So then it has a Mattia class, it's in X1 E tensor omega 1 of Y, and it's the extension class of the jet bundle. So you have jet sheaf. If E is a vector bundle, it will be the extension class of the jet bundle. So and so okay, so we have the Attia class, and then I'm describing something next called the semi-regularity mesh. So this is an ingredient given Q between 1 and n minus 2. Let sigma Q be the composition, the Polar composition. So you start with x2 of EE, and then you can take powers of that Tia class. So powers will be in higher x of E and E tensor power of omega, and then you can project to the wedge power. So the Tia class, maybe I'll write it here. The Tia class of E to the cubed power is an element of x q E tensor omega q of y. And now you can compose two extensions with it, and you'll increase the degree of the extension. So if you take the Tia class to the cubed power, and you know that if you take the sum of these to the divided by q factorial, and you take the sum, it's called the exponential Tia class, and its trace is the Chern character of E. And so this is related. So you divide by q factorial for that reason, and you end up in x 2 plus q E tensor omega q of y, and then you just take the trace along E, and you end up in a Dolbeault homology. And so this composition is sigma sub q, and then the semi-regularity map that by sigma E is just the collection of all these. So sigma E is sigma naught, sigma 1 up to sigma n minus 2, and it goes from x2 to the direct sum of the Dolbeault homology, which we are thinking about as sitting in the Bloch homology. This is 2, sitting in H star Y, and there's E is called semi-regular. The title had semi-regular sheaf. This is where we define them. E is semi-regular if the semi-regularity map is injective. I'll get back to maybe at the end the semi-regularity if I don't run out of time. But let's just observe the following: if n is 2, if y is a surface, then all you have is sigma naught, and sigma naught just so q is 0, and this sigma q is just a trace, and that's it. And now if y is a abelian surface or a K3 surface, then and E is simple, so by cell duality this is the same as Hom EE, and simple means that this is one-dimensional, then the trace is an isomorphism by cell duality, and also it's semi-regular. So the notion of semi-regularity sheaves is a generalization of the notion of simple sheaves on abelian and K3 surfaces, which are semi-regular. And Mukai has results about simple sheaves on K3 surfaces, and that's what Buchweitz and Flenner generalize in the following theorem. So theorem. So it's a generalization of Bloch's, and this version is by Buchweitz-Flenner. So we have y as above, E is a coherent sheaf, and it will be semi-regular. So so we have a Y, and suppose that we have a deformation of it. So we have a family. This morphism will be smooth and projective, and over a base. And for Buchweitz and Flenner take this to be a germ of a smooth analytic space. I'll take it to be smooth. Germ is fine, but it could also be simply connected and smooth analytic space. And so suppose that we have, and let E be a semi-regular sheaf on Y, suppose, so we want to extend E from Y to the family. And that will prove the algebraicity of its Chern class on all fibers. That's the main purpose. So suppose that the Chern character, this is clearly a necessary condition, remains, I'll explain, algebraic in all fibers of phi. Sorry, not algebraic. That's what we want to conclude. Remains of Hodge type. In all fibers of phi. So that's why I chose, since B is chosen to be simply connected, we have the local system, which is necessarily trivial, of cohomologies of the fibers. And by this, I mean that the flat section, flat global section through the Chern of E over the special point is of Hodge type in all fibers. Then, so that's the first, so the main part is that there exists, so E expands locally. There exists an open subset of the base, which is enabled of the special fiber and a coherent sheaf over the inverse image, flat over U. I won't write it, but it's flat over U, extending E. So in particular, the Chern character of E remains algebraic in all fibers of phi. Now, why? So certainly it remains algebraic, the Chern character of the restriction of E to fibers over points of U. But it is known that the locus where classes remains algebraic is a countable union of closed analytic subsets of the base. In fact, by Katani-Kaplan and the link Katani-Kaplan, it's even an algebraic locus. But in any case, if it contains an open analytic subset, it must be the whole of B. And now there is an extension of so this is Buchweitz-Flenner. There is an extension due to Pridham and Perry, Alex Perry, recently, which is Vito. So kappa of E, I'll define kappa of E to be the Chern character of E, tensor. So I'm assuming here that the rank of E is non-zero. The exponential of minus C1 of E, I'll explain, over the rank of E. remains algebraic if it remains of Hodge type. Okay, so let me explain. It could be that you chose E wrongly, but you tensored inadvertently by the line bundle whose first Chern class does not remain of Hodge type. Then you would like to correct it. So if the first Chern class of E is divisible by the rank, you can simply kill the first Chern class by tensoring by this line bundle. And in that case, this is another coherent sheaf. And this is the Chern character of another coherent sheaf, which is the corrected one. But the key point is that even if this is not integral, second cohomology, this can be done. You can tensor by square roots of line bundles. These are no longer real line bundles. They are called twisted sheaves. They are twisted line bundles, but there is a category of them, and they behave very similarly to coherent sheaves. And this would be the Chern character in this category, and you still kill the first Chern class. And if this remains algebraic, then everything goes. And we will need that version. So it's a technicality. All right, so we have the semi-regularity theorem. And now the next topic is yeah. So the next ingredient, the other ingredient is the importance of spin groups in the geometry of abelian varieties. So that's the next topic. This is the second main ingredient. So abelian varieties in spin groups. So let X be an abelian n-fold, and let X hat be the dual abelian variety, so it's a fixed knot of X. Our A, we will construct a complex multiplication on X times X hat, which is even dimensional, but N need not be even dimensional. Let V be the first integral cohomology of X cross X hat. So it's the direct sum of H1 X and H1 X hat, and this is naturally dual to this. Important for us. And so classes here are pairs. We will regard classes here as pairs alpha theta, where alpha is here and theta is here, and we regard theta as a linear function now. And so we have a pairing, integral symmetric bilinear pairing, where alpha 1, theta 1 paired with alpha 2, theta 2 is the obvious one, so it will be theta 1 of alpha 2 plus theta 2 of alpha 1. And notice that with respect to this pairing, each diagonal is maximal anisotropic, which will become important soon. And so if we have a pairing, then we have the orthogonal group of this lattice and a special orthogonal group, and there is a certain character called the Spigno norm. Its kernel is denoted with plus. It's an index to a subgroup. I will not get to another characterization is that it's the image of the spin group. And if you're uncomfortable with integral spin, just think about tensoring with Q. Then it's the usual spin. This is the vector representation of spin. And without Q, it's just the intersection of this with it's the inverse image of SO plus. But spin has also the spin representation. And I'll stick now to the integral version, the arithmetic subgroup. And now, how do you construct the spin representation? You take a maximal isotropic subspace of the vector representation, and you take its exterior algebra. But if you take the maximal isotropic to be the first isomer, the exterior algebra is just the cohomology of X. And so that's the spin representation. It goes to automorphisms of the total cohomology of X, integral cohomology, and it's actually maybe instead of it's the orthogonal group because it preserves a certain bilinear pairing, which for algebraic geometers, so these are denoted by S for spin, the spin representation, and of course it breaks into S plus like some S minus, where S plus is the even cohomology of X. And S minus will be the odd cohomology. This is the Mukai pairing. And it's simply the Poincaré pairing with a sign change. So alpha and beta, this is the integral over X of tau alpha cut product beta, where tau is the dualization. So tau acts on HI of X. This is the multiplication by -1 to the I minus 1 over 2. And what it does is if alpha is the Chern character of sheaf, then tau alpha would be the Chern character of the derived dual. So if it's a vector bundle, it's the Chern character of the dual vector bundle. So that's what is preserved by it. So it's known that, and in fact, it goes to S or even plus. And now there is a theorem due to Mukai, Polishchuk, and Orlov relating this spin group to derived equivalences of abelian varieties. So if you have so you see, if you have an equivalence of the derived category of X, it will act on the cohomology of X. But also, X cross X hat is a subgroup of the group of autoequivalences of the derived category. X acts on itself by automorphism translation, and X hat is peak knot, so it acts by tensoring by line bundles. And this is the identity component, so it's a normal subgroup. So the whole group of autoequivalences will act on it by conjugation. So the group of theorem due to in chronological order, first it depends on result of Mukai, then Polishchuk work and enhance it, and then the final version is due to Orlov. And I won't say precisely, but I say something correct. That's all we need. So let D mon, the monodromy group of X, this be the subgroup of the orthogonal group of the cohomology of X with the Mukai pairing, generated by the monodromy of X is SL H1 XZ, and the cohomological action, I'll write it by H for cohomology, action of all equivalences of the derived category of X for all possible complex structures on X. So then what is this group, the derived monodromy group? Then D mon X is, so it's a subgroup of the it's the image under the spin group. This is, by the way, a faithful representation. So it's essentially spin V. It's M of spin V. This arithmetic group. So, okay. So now that's where spin group come in. Now let's W inside V sub K. Oh, let K be, so K here, K is fix an imaginary quadratic number 2. And so what I'm going to do next is construct complex multiplication on X cross X hat. That's the special one where we did the algebraicity of the bell classes we did show. So we fix this AD, let W inside V sub K be now maximal isotropic, so half the dimension subspace satisfying we need two conditions. W intersect its conjugate is trivial, so these are transversal. And of course, we also want the condition. So W10 and W01 are n-dimensional. So the rank of B is 4n, right? Because X is n-dimensional, so the rank of H1 of X is 2 n-dimensional, so this is 4n. So here's the complex multiplication. It's easy. So let eta from K into the endomorphism, Hodge endomorphisms of VQ. This is H1 X cross X hat, the Q coefficient, right? B, so I'll call it eta sub W, it depends on W. So eta W of any element of K, and let me call it eta sub T. Maybe I don't need, yeah. This acts on W by multiplication by T, and it acts on W bar by multiplication by T bar. That's all. And I claim that it's certainly a Hodge endomorphism, but in fact, it's a priori it acts on V sub K, because W is, what did I write? W, yeah, V sub K. But in fact, it maps V sub Q, the subspace, to itself, right? Because this condition tells us that V sub Q is W plus W bar, where W is in W, right? It's self-conjugate. And so eta sub T acts on W plus W bar by TW plus d bar w bar, but this is just d w bar, so it maps dq to itself. So we have we have that x cos x hat and eta is an abelian variety of Weil-type. So we got complex multiplication. I'm slightly cheating it. There is one thing that it's not clear that there is yet a polarization compatible with it, but in the example I'll give, there will be. So, all right, so we have that. Okay, so let let spin B sub W inside spin V sub Q let this be the subgroup G such that rho sub G maps W to itself, and rho sub G restricted to W, the determinant is 1. So it acts trivially on the top wedge of W, and then this spin EQ sub W is the Mumford-Tate group of the generic A at a prime, the formation equivalent to our x cos x hat eta. So in fact, if you look at the cohomology of x cos x hat with q coefficient, and you look at the spin V sub W invariant subring, then this is generated by the unique. There will be a one-dimensional class in H2, and I assume that this is ample, and so powers of it maybe generated as an algebra, and the J classes. Okay, and all right. So the strategy. How do we combine the semi-regularity and these facts about spin group in the relationship to abelian varieties into a strategy to prove the algebraicity? So construct on x cos x hat coherent sheaf E. So we have this is now an abelian variety satisfied the following condition. First of all, we want it E semi-regular. Two, we want the Chern character, or more generally, the kappa class of E, this normalized Chern character, to be we want it to remain of Hodge type. This is the only condition in the semi-regularity theorem. So we want it to remain of Hodge type under all the formations of x cross x hat and eta as an abelian variety of Weil-type. But by this condition, we want it to be spin V sub W invariant. Invariant in the Mumford-Tate group, so it will remain of Hodge type. And three, we want this shift to be interesting. So if you take the middle cohomology of this normalized Chern character, so this is in H2n of x cos x hat, and this H is the class in H2 which is invariant under this. to the power n, these two are linearly independent. So I claim that if we can implement that, we are done. So let me explain why. Such a sheaf will give you the main theorem that all the V classes of all abelian sixfolds, or abelian 2 and folds, the formation equivalent to x cross x hat, and eta, the V classes are algebraic. Why? Because you see, 1 plus 2 plus the semi-regularity theorem imply, maybe let's say just 1 plus 2 without this, yeah. And the semi-regularity theorem gives you that kappa of E remains algebraic on all abelian varieties of Weil-type, the formation equivalent to x cross x hat at H, because by the semi-regularity theorem, because it is semi-regular and it remains of Hodge type. And this implies that if you take the middle chunk class in the middle cohomology, this belongs to the only classes that remain of Hodge type. So this belongs to the span of H to the n, direct sum the V classes on x cross x hat eta. So it follows that this is equal to type t is some rational number times h to the n plus gamma, where this is a V class on x cross x hat, and now 3 implies that gamma is non-zero, and this remains algebraic, and but the polarization in algebraic by this is still on 1-1 classes. So gamma remains algebraic. Algebraic on all abelian varieties of Weil-type in this connected component. And it's non-zero by part 3. So K, we have still the action of K via correspondences. Time gamma remains algebraic, because K acts via algebraic correspondences, but this is W A eta prime. Well, it's W. Well, if this is this gamma prime now, it's the flat deformation of gamma to here. To gamma prime here, you have a non-zero algebraic class of Weil-type in each, and if one non-zero algebraic Weil class is algebraic, then all are, because you can sweep all of them by the action of K. And so, so if we can implement this strategy, we are done. Now, I started at when did I start? 4:30?
Yeah.
Okay, April. All right. So we need to talk about pure spinors. So there is a basic fact about the action of the spin group, which is that pure spinors. So fact, if you look at the projectivization of H naught of X, this is now a point in the projectivization of the even cohomology of X, the complex coefficient. This is projectivization of the half spin representation. So we have a point. The stabilizer in spin v sub c of this point is equal to the stabilizer of, now I hope I didn't erase it. You see this v is h1 x times some h1 x hat. So when you complexify, then you have, this is a maximal isotropic subspace of V, so it's the stabilizer of the projectivization of H1 x hat in the Grassmannian of two-dimensional maximal isotropic subspace. I is for isotropic in VC. So this is a fact, and but this is the homogeneous space. And so that what this means is that the orbit of this point under spin is isomorphic to this, because the stabilizers are the same. So we get an embedding of the Grassmannian of maximal isotropic subspaces into the projectivization of the even cohomology of X. And the image is the even spinoidal variety. And the point in the image, L of W, the W is the maximal isotropic subspace, is called a pure spinor. Now we saw that for a maximal isotropic subspace W, we construct complex multiplication. And so, example, oh, I shouldn't have put this strategy, but anyway. For example, let theta, this is theta, be, let's say, an ample 1-1 class ample. It will, we don't need, later we'll need it to be ample. Then if you take the exponential of theta, so, 1 plus theta squared over 2, and cut product, this is in automorphism of the cohomology of X, actually with Z coefficient. So this is equal to mg for some g in spin V. M is the spin representation. And similarly, if you take x of square root of minus d times theta, cut product as an operator, then this is equal to mg for some g in spin v sub k. And so in particular, x of square root of minus d theta is a pure spinor, because if you act on 1, this is precisely the orbit. 1 is this. So 1 is the point spanning this line. So if you plug in on 1, you get an element in the image. You get a pure spinor. So this is L of some W. This is the W we will use. It's defined over K because this point is defined over K. This is all defined over Q. This L. And so what is this? So this is equal to 1 plus square root of minus d theta minus d theta square over 2 plus dot 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 plus, and here we'll have minus d, so we'll have this, the cube root of this will be square root of minus d times d over 3 factorial theta cube plus dot dot dot. I'll call this class without the square root of d beta. I want it to be a rational class. This is alpha, and we'll let p be the span over q of alpha and beta. Then the projectivization of the complexification of C. So if you complexify, you get a two-dimensional complex subspace. This you get a line. This is a secant. This is where the secant comes in. Secant to the spinorial variety. Oh, this is the embedding over there. It hits it at this, and it's a complex conjugate. And now, so we will consider x cos x hat with the complex multiplication given by this w, and we want to construct a coherent sheaf satisfying the strategy that we laid out. One important thing is that if you let spin v q sub p inside spin v q be, let this be g such that m of g, the spin representation, takes p to itself, and it restricts to p as the identity. Can I have 2 minutes? Then the key point is that spin VQ sub P is equal to what we had before. It's again the Mumford-Tate group. It's kind of obvious why if you work it out. And so now we want to construct a coherent sheaf on x cos x hat, which is essentially with an invariant Chern character normalized. It is easy to construct on first on x cross x coherent sheaf with spin v sub p invariant, let's call it E, Chern of E. Simply let, so we have x cross x, and we have the two projection, and pi 2, and let F1 and F2 be coherent sheaves on X with shared character in P. These are what I appear to be in the title, the secant sheaves. So P is the secant, it's the plane, but if you projectivize it, it's the line, and secant to the spinorial variety. Suppose that these are coherent sheaves where the shared character is in P. Then if you take F1, pi 1 upper star of F1 tensor pi 2 upper star of F2, call it F1 box product F2. Its shared character in x cos x under the diagonal action of spin V is invariant because by construction, because P, this acts as the identity. And so what we need is to transform this to x cos x set. Let me give you an example, the main example, and then I'll stop. So so I need to give you an example of such an F1 and F2, which I use for, that's the only place where I specialize to 3-dimension. So let P be a curve of genus 3. and X will be the Jacobian. We will let Pi in X, I will need P plus one of them, where our K is Q squared of minus D. It's the same D. For each K, I need a sheaf. The images of the Abel Jacobi translate generic. Translate of the Abel Jacobi image of C. And we also have the theta line by the ln X after translation. And so take F1 to be the ideal sheaf of the union. They are disjoint if they are generic. P plus one of the CIs twisted by theta. If you check what is the Chern character of F1, well, this is rank 1. The first Chern class is theta. Now, if we didn't have theta, then you'll have minus the D plus 1 times the class of CI, which is theta squared over 2. So it's minus, but since you are tensoring by theta, you have minus D over 2 theta squared. That's it. And here, if you calculate, you'll find that this is minus D over 3 factorial theta cubed. And this is precisely the class alpha, and this is the class beta that span P. So this is a secant sheaf. It's a sheaf whose Chern character is in P. And we'll take F2 to be, I don't have time, but we'll take C prime to be the translate of minus the Abel Jacobi curve, and then we'll form the same thing, and this will be F2. And now I need to tell you, the only thing I need to do is tell you how to transform to X cross X hat. So the point is I don't have time, but this is Orlov's derived equivalence. There is a derived equivalence from X cross X to X cross X hat. Now the point is that on the level of cohomology, you get an isomorphism. Now notice that this is the top wedge of the vector representation of spin V, and this is the tensor square of the spin representation of spin V. And it's known that if you tensor with Q, these are isomorphic representations, but they are not over the they are not isomorphic as integral representation, but I tweak it. The point is that this is almost, and if you tweak it, it becomes spin V equivariant. And so if you have here a sheaf whose Chern character is invariant under a subgroup, the Mumford-Tate group, the subgroup of spin V, the image will be an object. It could turn out to be a sheaf for a lot of work, who's invariant also under the same thing, because this is spin V equivariant. And that's the end of the strategy once you put it together. I apologize if I don't have time.
Are there any questions?